Okay, we are back again. So, next is leading power factor load, right. So, the way we have done lagging power factor load, same way we will do it your leading power factor load. In this case current is leading, right. Look, that E2 square is equal to, I did not do it for you, this is your job, that you please do it, I have made the approximation one, right. So, this is my current is, this is my V2, so I2 current is leading, the voltage I2 is leading voltage V2. So, this is my E2. So, this is my, this angle angle phi 2 is between I2 and V2, and angle delta is between E2 and V2, everything is clearly marked, right. So, take your what you call the horizontal projection, therefore, E2 cos delta will be V2, right. I mean it will be this E2 cos delta, right, I mean this one, right, whatever this thing, this one we take. So, E2 cos delta will be V2, first to make it like this V2 plus this one is I2 Re2 cos phi 2, because this angle is marked here phi 2, right, and this is going like this. So, take its projection, right. So, that will be then you have to subtract it, right. So, it will be minus I2 Xe2 sin phi 2, right, because you what to call, you have to find out E2 your cos your delta. So, it will be first to make V2 plus this one, then this one you also find it out how much it is. So, it is minus I2 Xe2 sin phi 2, right. So, just 1 minute. So, that, and we assume delta is equal to 0. So, cos delta is equal to 1, right. So, E2 minus V2 upon V2 is equal to, same way we will do it, I2 upon V2 Re2 cos phi 2 minus Xe2 sin phi 2. So, V2 0 minus V2 upon V2 will be actually is equal to, same way that ZB2 is equal to V2 upon I2. So, you will get Re2 per unit cos phi 2 minus Xe2 per unit sin phi 2, right. So, if it is your what you call that in general that for lagging power factor sin is plus for regulation, for leading power factor sin is minus, right. And other thing if you do that your what you call that your that unity power factor, let me go to that your unity power factor load, the regulation, right, here it is, here that means here also, here look, here also you can write, no, this one is equal to Re2 divided by V2 upon I2. So, my this is my Re2 divided by ZB2, this is actually is equal to Re2 per unit, right, and unity power factor load. So, cos phi is equal to 1, right. So, that means in general that formula of the regulation, right, formula of the voltage regulation of a transformer. So, in general it will be, I am making it here for you, it will be Re2 then per unit cos phi 2, I can write plus minus, then Xe2 per unit sin phi 2. If it is a lagging power factor, if it is a unity power factor, your cos phi 2 is equal to 1 and sin phi 2 is equal to 0, right. So, phi 2 is equal to 0, it will be simply Re2 per unit, right. And if it is a lagging power factor, it will be plus this term, if it is a leading power factor, it will be minus, right. This you have to keep it in your mind in general. So, if you remember this only this formula. So, for unity power factor phi 2 is 0, right. For lagging power factor the sign should be your what you call plus, right, and for leading power factor sign should be minus, right. So, this is for your this thing. Next is polarity test. Here that how will test the polarity in your laboratory, when you will do it, definitely you will do like this. So, suppose this is polarity test. So, A1 A2 low voltage winding and capital A1 capital A2 is high voltage winding, this thing is given, right. So, one thing is there, suppose this polarity is marked like this, A1 A2 it is plus, the A2 is plus, here it is minus, here capital A2 plus and capital A1 minus, this voltage is V1 and this is V2 and one voltmeter is connected your across capital A1 and small a1, and this is the polarity the way it is marked, right. Now, if V1 it is difference operator I am using, V1 it is difference, of course a difference operator V2, right. Why I have made this symbol, this is I am giving you a small exercise, that why I am writing V1 difference your V2 the difference operator, it is actually like tilde, right. So, this one it written as, and if it is like this, right, then the polarities of the winding are as marked in the diagram. If you get like this, then you, but why I have used difference operator, right? Then the polarity as it is marked, you what you call in the diagram, it will remain as it is, it will not change, it is unchanged. If you get the reading of the voltmeter is like this, if you get like that, but why I have used difference operator, it is a small your what you call exercise for you, right? And if you get your V is equal to V 1 plus V 2, right. So, everything is marked actually. If you get V 1 plus V 2, then the polarity margins of one of the winding must be interchanged, either this side or this side, you just interchange, right. Then your what you call your then if you get V is equal to V 1 plus V 2, I mean if it is additive, right. So, then the polarity margins of one of the windings must be interchanged. So, this is all for polarity test, nothing is there actually, right. Now, open circuit test to obtain RC and XM, that means for the transformer we have to find out the your what you call the parameters, right, particularly RC, XM, R1, X1, R2, X2, all these things we need to obtain. So, generally open circuit test we for to obtain RC and XM, that is a we call shunt parameter, because these are connected in parallel, these are shunt parameters, right. We perform actually open circuit test. Now, for open circuit test what we have to do is you need you have to connect one ammeter, one wattmeter is there, and secondary side, that high voltage side actually remain open. Actually in the laboratory actually this open circuit test or short circuit test, whatever it is, it can be performed on either side, right. But in the laboratory, right, that generally we perform that this one on LV side, your what you call the supply that your open circuit test we perform on the LV side and not on the high voltage side, right. So, but either side it can be done, either side. Sometimes suppose that voltage level may not be available, right. So, because that your what you call the high voltage may not be available in the laboratory, that is why we perform your what you call open circuit test, your what you call this on the your low voltage side. So, this is the low voltage side for open circuit test, right. But short circuit test in the laboratory we perform on the high voltage side, but let me tell you one thing, it can be done on either side, you will get the same result, right. So, this is the ammeter is connected, one wattmeter is connected and one voltmeter is here, and the supply voltage is V 1, right. So, if you supply is given to L voltage side, and you have to suppose in the laboratory you have 110 by 220 volt, suppose your transformer is 110 by 220 volt in the laboratory say, then low voltage side is 110 volt and high voltage side is your what you call 220 volt. Then on low voltage side 110 volt is given, this side actually 110 volt is given. Suppose for example, if this low voltage side is 110 volt and high voltage side suppose transformer you have 2000 volt 2 kV, in the laboratory the 2 kV may not be available, right. That is because for open circuit test you need full voltage, that is why you perform open circuit test on the low voltage side in the laboratory, but either side it is possible, I mean you will get the same result, same parameters value RC and XM. So, your what you call that wattmeter reading is actually in that case wattmeter, this side is open, that is secondary is open, there is no load on the secondary, it is written open circuit, right. So, whatever wattmeter will give, it will basically give you the coal loss, right. That is your in the task, because an open circuit is carries no load current, right, and ammeter will give you the I0, the no load current, and wattmeter will give the no load power loss, right, and this is the voltage you are giving 110 volt. So, in that case everything is written here, ammeter will give no load current I0 and your voltmeter will be your applied voltage is V 1. So, this wattmeter reading is known, ammeter current I0 is known, supply voltage V 1 is also known, therefore, you can get phi 0. Therefore, V 1 I0 cos phi 0 is equal to Wi, that means cos phi 0 is equal to Wi upon V 1 I0 as a no load power factor, right, and therefore, if you get cos phi 0, so IC will get I0 cos phi 0 we have seen before, I will get I0 sin phi 0 you will get it, right. Therefore, your equivalent circuit say this is R1 and X1, this is the current I0, this side is your what you call that your what you call that your secondary side is open circuited. So, nothing is drawn after this, right, nothing is drawn, R1 and X1 put it here and this is the current I0. Therefore, your what you call RC will be V 1 upon IC, and IC you have got it because cos phi 0 you got it, IC you know, I0 you know, cos phi 0 you know. Therefore, RC will be V1 upon IC, that is V1 upon I0 cos phi 0. Similarly, XM will be V1 upon IM. So, V1 upon I0 sin phi 0. Actually, this I0 current is very small and the winding resistance of the transformer is also very small. Therefore, this loss your what you call at your no load, the winding loss in the transformer is negligible, right. Therefore, this is the circuit, but equivalent circuit as seen from this, when this R1 X1 say it is not there, neglected. Therefore, this is the equivalent circuit for no load, right, and everything is marked by an arrow, right. So, that is I0 square R1 no load copper loss is very small, negligible, right, and you here wattmeter reading gives only the iron or coal loss. So, what for your what you call for open circuit test. Now, so the voltage drop across R1 plus Jx1 is negligible because I0 is very small, right. So, this is your approximate circuit. Now, short circuit test to obtain the series parameter, that is your resistance and reactance. Now, actually in a transformer, then now this is the short circuit test. Short circuit test is performed on the high voltage side, because when we perform the short circuit test, that we need hardly 5 to 8% of the total your voltage on the high voltage side, right, to flow the your what you call the rated current or full load current. Say the secondary is the your what you call low voltage side is the short circuit, not secondary is low voltage side is the short circuited, right. So, to allow that your full load current to flow or rated current to flow, this short circuit, this low voltage side it needs very small voltage, right, maybe 5 to 8% of the rated voltage on the high voltage side. So, it is written here very low voltage supply, and this is VSC. So, this supply is given for your what you call for an instrument called variac, variable AC supply. Just if you just move it like this, then fuse will blow, right, because it will draw huge current. So, this is my short circuit current, this is the voltmeter is connected, wattmeter is connected, and this is ammeter, and this is the your what you call that the low voltage side you short circuit, it is shorted, right. Now, in this case 5 to 8% of the rated voltage is required to flow that your full load current or your rated current. So, as a result, the exciting your what you call current under short circuit condition 0.1 to 0.5% of the full load current. So, exciting current means I0, so that is negligible, very small, right, and transformer resistance and leakage reactance are very small. Here 5 to 8% of rated voltage is sufficient to circulate the full load current, because it is short circuited, right, and transformer resistance and leakage reactance is very small, right. So, wattmeter reading actually will give you the copper loss, and this is the ammeter reading will that is give the your what you call full load current. So, in this case, if it is suppose 100 220 volt, so and say transformer for example, if it is 2.2 kVA transformer, so high voltage side actually 220 volt. So, short circuit voltage you need 5 to 8% of 220 volt, that means your 5 to 8% means roughly your 5% of 220 volt means hardly 11 volt. So, if your what you call if your 11 volt about 11 volt you supply a rated current, that is the full load current, that is 2.2 kVA transformer. So, 2.2000 by high voltage side voltage is 220. So, 10 ampere, that means you will allow that 10 ampere current should flow, right, and for if you 5% is 11 volt. So, around 11, 12 or 13 volt you will find that 10 ampere current is flowing. So, that variac you have to move it very slowly, if you move it very fast then fuse will blow. Again you have to your what you call again you have to switch off the supply and you have to reconnect the fuse wire, right. Therefore, this is the equivalent circuit we have studied for a transformer, right, and this is the short circuit current and this is I0 this thing, but this your what you call this I0 is very small percentage of ISC. So, this term we will neglect, this loss in the RC we actually will neglect, right, what in the wattmeter reading, that is equivalent circuit under short circuit condition. If you neglect this part, because this loss here it will be very negligible here, very negligible. So, that means it will be a simple series circuit, right, simple series circuit. So, you will get your R1 X1 R2 X2 are all in series, right. So, this is the approximate equivalent circuit under short circuit condition. So, voltage is equal to VSC, current is equal to ISC and power is equal to WSC, that is the copper loss, ISC is the full load current and VSC is the voltage what I told you required under short circuit condition to the low voltage side, that is 5 to 8%, right. So, that means Z is equal to now VSC upon ISC, that is the impedance of the transformer we will get, that is root over R square plus X square, right. Actually, R is equal to R1 plus R2 and X is equal to X1 plus X2, right. Another thing you know that ISC square R, the copper loss, is equal to what meter reading, because total R is R1 plus R2. So, ISC square R is equal to WSC, the watt meter reading, right. Therefore, R is equal to WSC upon ISC square. So, we get R1 plus R2, right. These values all are referred to high voltage side, because short circuit test is performed on the high voltage side, right. Therefore, this is my Z we got. So, this is x is equal to then root over z square minus r square, right. But z is your what we call x also is equal to x1 plus x2 together, r also r1 plus r2 together, right. But so how we will separate this, right. So, generally resistance could be separated out by making DC measurement on the primary and secondary, and duly you are correcting this for AC values. This one I am not doing in this video course, but I am telling you that from you try to find out that how to find out the resistance. Suppose if it is asked that each side of the transformer winding you measure the resistance, right. How you will do this? That resistance could be separated out by making DC measurement, right, on the primary and secondary, and duly correcting those for AC values. This you try to do it now of your own, right. That and another thing is that your reactances cannot be separated as such, right. But where you are required, this could be equally you are approximated to the primary and secondary side. For a well designed transformer, generally reactances x1 is equal to x2 referred to any side, right. This is sufficiently accurate for a well designed transformer. And for R1 R2, just an exercise for you, just you see you put it in the forum that sir we are doing like this, and we will give the answer whether you are correct or not, right. So, another thing, numericals will come later. Another thing is auto transformer, that your what you call that basically it is your two winding transformer, right, auto transformer. So for whatever I have talked now, something I have said also. One example is also not mention auto transformer, but some instrument name I have taken. So, you tell me, give one example of auto transformer, right, where auto transformer is being used, right. So, something I have written perhaps, right. For two winding transformers, the windings are electrically isolated, that we have seen, right. In a two winding transformer, all volt ampere is transferred magnetically, that also we have seen for single phase transformer. When the primary and secondary windings are electrically connected, so that part of the winding is common to both, the transformer is known as auto transformer. That is actually primary and secondary, that is your what you call windings are electrically connected to that part of the winding is common to both, right. In that case we call it as auto transformer. For example, applications, here something is written that induction motor starters, variable voltage power supply, that is variac, right, just I mentioned, and your low voltage and current levels, right. So, basically if you consider like this, first little bit we have to understand, there should not be any confusion. Before doing anything, I am just trying to tell you, suppose this is only one winding is there, that you can see only one winding. Now, for example, if I want it is a two winding transformer, then what we will do, this one we consider as one winding and this one you consider as another winding, right, for two winding transformer, as if this is one, as if this way you imagine. So, if you consider this part, so current is flowing here is I1, right, and if you consider this part, it is I2 minus I1, right. This way, that means this is as if this part is one winding and this part is one winding, like a two winding transformer, whatever we have studied there just now, whatever we have studied so far, right. So, in that case, your what you call, this is the current flowing your through this is I1, and current, suppose if load is connected, this is I2, and this if you take in this direction, current will be I1 minus I2, but I have taken in this direction. So, it will be I2 minus I1, right. So, from A to C, this is A and this is total winding, number of turns is N1, and for B to C, number of turns is A2, and current flowing A to B is I1 and your C to B in this direction is I2 minus I1, and this is the current I1 and this is the voltage V1 and this is the voltage V2, right, same as whatever. But when we consider two winding transformer, as if this is one winding and as if this is another winding, when this is auto transformer, we will make it different way, right. So, in this case, so this is an auto transformer, but we have to compare these two, right. So, in this case, so auto transformer has your what you call some lower reactance, lower losses, smaller exciting current and better voltage regulation compared to two winding your counterpart, right. So, primary turns N1, I told you winding section AC with N2 turns tap for a lower voltage secondary winding section BC, this I told you. Now, two winding voltage and turns ratio, right. So, for two winding voltage I told you that this for two winding transformer, this is one winding, right, this is one winding, this voltage is V1, this voltage is V2. So, that means this voltage is V1 minus V2, I mean here this voltage is V1 minus V2 and this is my V2, right. If it is a two winding transformer, therefore, my K actually will be equal to V1 minus V2 by V2 for two winding transformer. That means, this one can be written as N1 minus N2 divided by N2, right. This only this portion you have to understand here, there should not be any confusion, right. So, in this case, same I am writing K is equal to V1 minus V2 upon V2, N1 minus N2 upon N2, of course, N1 greater than N2. Now, when you take auto transformer, as an auto transformer, is voltage and turns ratio will be K dash is equal to V1 upon V2. For auto transformer, the same winding you are using for both, right. So, for auto transformer, this is your one turn, that is your N1, and this is another turn, same winding, something we are tapping it out, right, same winding. So, voltage is V2, right. So, for auto transformer, suppose K dash is equal to say V1 by V2 is equal to N1 upon N2, right. When you are taking is auto transformer, this full transformer, and part of this we are that voltage we are tapped from this your what to call from some part, say between A and C, that is B and C, right. So, in this case, your K dash is equal to V1 upon V2 is equal to N1 upon N2, that is greater than 1, because N1 greater than N2 from the diagram. Therefore, K dash, it was V1 minus V2, that K dash can be written as you add V2 subtract V2. So, K dash is equal to V1 minus V2 upon V2, sorry, V1 minus V2 plus V2 upon V2, right. But so, this can be written as V1 minus V2 upon V2 plus 1, because V2 by V2 is 1. Therefore, V1 minus V2 upon V2 is equal to K. So, K dash is equal to K plus K1. This is the relationship between the auto transformer turns ratio and the two winding transformer ratio, the way we have considered it, right. Now, let us compare volt ampere rating of the two, right. As a two winding transformer, I told you the voltage is your what, it TW stands for two winding, TW stands for two winding. So, voltage for two winding transformer, that your V1 minus V2 into I1 is equal to I2 minus I1 into V2, as if you go like this, as if this is one winding, this is your one winding. So, as if it your and voltage here total is V1, this is V2. So, voltage here V1 minus V2 and current flowing through this is I1. This is the volt ampere rating for this winding, as if two windings are separate, this way you imagine, and this is another winding is there, voltage is V2 into your I2 minus I1, right, both have to be same because rating, volt ampere rating, as if this is one winding, as if this is another winding, I mean it is like this, it is like this, and here it is voltage, for this one voltage is your V1 minus V2 and current is your I1, and here voltage is V2, current is I2 minus I1, this way you imagine, right. So, that is why it is V1 minus V2 into I1 is equal to I2 minus I1 into V2. When used as an auto transformer, so volt ampere will be auto will be V1 into I1, because same winding are using. So, for auto transformer, right, for auto transformer, this is the whole winding, that as if this way you think primary and secondary, right. So, for auto transformer, if you take this is the V1 and current is I1, say V1 I1, right, and output your output you are taking V2 into your what you call your this thing, your I2 minus I1, right. So, in this case, for auto transformer, your sorry V1 I1 is equal to V2 minus V2 I2. Actually, here hold on, for auto transformer input, I have to see the input here, this is the whole winding. So, input here is V1 I1 and output here is current is I2. So, this is V2 is equal to V2 I2, right, because this is the current I2 going to the load and voltage your here it is V2. So, if it is ideal case only, so it is V2 into I2 is equal to V1 into I1 as an auto transformer, right. So, this is an auto transformer. Therefore, we can write V8 winding transformer is equal to, we can write your this your here if you come that V A two winding transformer V 1 minus V 2 into I 1 this one. So, divide numerator and denominator by V 1 here you divide. If you do so, it will be V 1 minus V 2 upon V 1 into V 1 I 1, right, or V A two winding transformer is equal to this bracket part, you can write 1 minus V 2 upon V 1 into V 1 I 1, or you can write V 2 by V 1 is equal to N 2 by N 1, 1 minus N 2 upon N 1, and V 1 I 1, that is volt ampere rating of the auto transformer, that is V A auto, right, because it is V 1 I 1 is equal to V 2 I 2. So, it is our V A auto transformer. Therefore, if you simplify all these things, right, that V A this one your what you call this N 1 minus N 2 upon N 1. So, numerator and denominator this term you numerator denominator this term you multiply by N 2. Therefore, what will happen, you can write N 1 minus N 2 upon N 2 into N 2 upon N 1 volt ampere auto, right. Therefore, this N 1 minus N 2 upon N 2 your what you call your into N 2 minus N 1 is nothing but K upon K dash V A auto. This portion please do it, all these thing relationship is given that K dash is equal to your K plus 1. So, there you use all this relationship. So, you will get V A two winding transformer is equal to K by K dash your what you call V A auto, right. So, this your this is your K and K dash is equal to already given N 1 upon N 2. So, it is K upon K dash V A auto, right, or you can write V A auto is equal to your K dash is equal to you have put K plus 1, because we have seen earlier K dash is equal to K plus 1 cross multiply, right, but and put K dash is equal to K plus 1. So, V A auto will be K plus 1 upon K into V A two winding transformer, or V A auto will be 1 plus K is equal to V A two winding transformer. That means, V A auto is greater than your V A two winding transformer, that is volt ampere rating of the auto transformer greater than your volt ampere rating of the two winding transformer, right, because your K is greater your what you call K is always your what you call greater than 0, right. So, naturally, V A auto will be greater than V A two winding transformer. With this your single phase transformer is over, only we will see few numericals, right, and this is very simple thing and nothing is there, just there should not be any confusion of auto transformer, very simple thing, right. So, take one example, the parameters of approximate equivalent circuit of a 4 kVA 200 by 400 volt 50 Hz single phase transformer. These are the parameters given, RE is equal to XC and RC is equal to given 600 ohm, XM is given, right. Now, when rated voltage of 200 volt is applied to the primary, a current 10 ampere 0.8 power factor lagging flows in the secondary winding, you have to calculate. So, this is your problem, right. When rated voltage of 200 volt is applied to the primary, a current of 10 ampere 0.8 power factor lagging your flows in the secondary winding, you have to calculate current in the primary, terminal voltage at the secondary side, it is very simple. This is the circuit, right. So, this is your my equivalent circuit RE 1 XE 1, right. This is your what you call this side is load is given. So, everything is your in terms of primary side. So, in that case your now when you earlier we have seen it, no, when you transform this to that side, it will become your V 2 dash is equal to K V 2 and dash line shows the load. Earlier we have seen this circuit, this side 200 volt, parameters are given RE 1 XE 1 RC XM all are given. So, I 2 is given also 10 ampere, right, I 2 is given 10 ampere at 0.8 power factor lagging. So, I 2 is on the secondary side. So, I 2 dash you have to bring it to the refer to the primary side. So, I 2 dash will be I 2 into N 2 upon N 1, because N 1 I 2 dash is equal to N 2 I 2. So, I 2 dash is equal to this much. So, I 2 dash will become 20 ampere at 0.8 power factor lagging, right, that is 36.87 degree lagging. So, that means, I 2 dash will be 16 minus J 12 ampere directly. Now, it is understandable. So, directly we are writing, and I C will be 200 by 600, because RC is 600 ohm, terminal voltage is 200. So, this much, and I M is equal to 200 by 300 this much, right. So, I C I 0 is equal to I C minus your J I M. So, this is the current that is no load current I 0. Therefore, I 1 is equal to I 0 plus I 2 dash. You just add these two, you will get I 1 is equal to 20.67 angle minus 37.8 degree ampere, right. And V 2 dash we know this earlier we have solved problems, we have seen the derivation also. V 2 dash will be V 1 minus I 2 dash R E 1 plus J X E 1, right. So, in that case you will get V 2 dash after solving you will get your 193.2 angle minus 1.2 degree, and we know that your what you call this volt, and you know V2 dash is equal to KV2, we know that. So, V2 will be your what you call 386.4 angle minus 1.2 degree volt, because your K is equal to your half, right. So, that voltage ratio is given 200 by your what you call 400, right. So, this problem is a simple problem. Now, example 11, a transformer has its maximum efficiency of 0.98 at 15 kVA at unity power factor. During the day it is loaded as follows, right. So, because we have to find out all day efficiency. So, for 10 hour it was 3 kilowatt, power factor 0.6, right. Lagging, it is generally lagging, but not mentioned here, right. So, 5 hour 10 kilowatt, power factor is 0.8, right, and your 5 hour 18 kilowatt, power factor 0.9, and 4 hour at no load. So, total if you add it is 24 hours, right, and find all day efficiency. So, 10 hour 3 kilowatt. So, basically 3 kilowatt into 10 means 30 kilowatt hour, right. So, similarly like this. So, maximum efficiency of transformer is 0.98, that is given. Now, load at which the maximum efficiency occurs, that is 15 kVA at unity power factor, that is given. That maximum efficiency of 0.98 at 15 kVA at unity power factor, that means my at maximum efficiency iron loss is equal to copper loss, that we have derived. We know that for maximum efficiency nu zeta max is equal to XPFL upon XPFL plus 2 Wi, that we have derived, that is output by output plus 2 Wi, right. Now, output is equal to 15 kVA at unity power factor. So, 15 into 1000 into 1, that is your this much of watt, because multiplied by 1000 divided by 15 into 1000 into 1 plus 2 Wi is equal to 0.98, because maximum efficiency 0.98, from which we will get Wi is equal to 153 watt. So, 0.153 kilowatt. Therefore, copper loss at your maximum efficiency iron loss is equal to your copper loss, right. So, it is your 0.153 kilowatt, right. Now, interval 1, that is 10 hours, load is 3 by 0.6, that is 5 kVA, right, because power factor is 0.6 and is 3 kilowatt. So, 5 kVA. So, copper loss we have to find out at this load. Copper loss is proportional to the square of the load. So, this you will keep in mind. Your rated kVA is 15 is given, and at that time load is 5. So, it will be 5 by 15 square into 0.153. So, it is 0.017 kilowatt, right, because copper loss varying with the load. So, at that time you find, because this is kilowatt divided by power factor will give you kVA, right. So, this similarly that energy loss will be 0.017 into 10. So, that is 0.17 kilowatt hour, right. So, this is your what you call that energy loss. Similarly, if you just look into this, right, so 3 kilowatt power factor is given, it is 10 hour. So, if you just your what you call that load was 3 kilowatt. So, we converted it to your kVA, and it is depend on the square of the load at that time, what is the your what you call in that your what you call that energy loss, right. But if it is a simple load, nothing is given. So, 3 kilowatt into 10 means it will be your what you call 30 kilowatt hour, right. Little bit we have seen at the beginning, I think, right, for the DC circuit analysis something we have seen. So, similarly, your interval 2 5 hours. So, load is 12.5 kVA, because 10 by 0.8 is the power factor. So, copper loss will be 12.5 upon 15 square into 0.153. So, 0.1042 kilowatt. So, energy loss will be 5 into 0.1042, that is 0.521 kilowatt hour, right. Similarly, interval 3 power factor is 0.9 and it is 18 kilowatt. So, 18 upon 0.9, so 20 kilovolt ampere. So, at that time copper loss will be 20 upon 15, that means transformer is overloaded. If rating is 15, that is 20, that means transformer is overloaded, right. So, 20 by 15 square into 0.153, so 0.272 kilowatt. So, it is energy loss will be 5 into 0.272, so 1.36 kilowatt hour. So, interval 4 hours no load, copper loss is 0, energy loss is 0. Now, energy loss due to iron loss plus during the whole day. So, 0.153, because iron loss 0.153 and 24 hours multiply, it will be 3.672 kilowatt hour. Therefore, energy loss due to copper loss during the whole day, you add 0.17 plus 0.521 plus 1.36, 2.051 kilowatt hour. So, total energy loss. So, due to copper loss and iron loss you add that is 2.051 plus 3.672, right. Total output during the whole day. So, it is your 3 into 10 there is the output plus 10 into 5 plus 18 into 5. I told you that initially 10 into 30 kilowatt hour, 5 into 10 and plus 18 into 5. This is the output and this is the copper loss, right. So, it is 170 kilowatt hour. So, output your efficiency is equal to all day will be output by output plus losses. So, this is output is 170 and this is my your copper loss and this is my in terms of energy. So, it will become 96.7%, right. So, so this is your some one or two more examples are there like auto transformer and your what you call this thing we will see in the next video lecture. So, thank you very much.